delve into a bit more detail on pattern and process and pick up where Paul left off. But first I'm going to get us into more of the fuels outlook, and I'm sure you've had information on this so far in the conference, but I wanted to reiterate some critical things about the climate outlook. Basically, what we saw last year, we're going to experience something similar to that, if not worse, in the future, based on all the ensemble of climate change models. Some models are suggesting wetter winters, which leads to abundant herbaceous grass growth. We've seen that again this year. We had a nice long wet winter, warm spring, and lots of herbaceous growth again. Higher temperatures over longer periods of the spring and summer, longer fire seasons are the result of that. Higher incidence of stationary blocking high pressure systems, and with that tends to come very strong gradient winds, strong wind events. And unfortunately, some pretty interesting research from Mike Flanagan. I don't know if he mentioned it earlier this week, but increased lightning. Some of his research suggests that for every 1 degree C increase in temperature, there'll be a corresponding 12% increase in lightning activity. So not great news on the climate side. And the models are suggesting that by 2030, certainly we're likely to see burned area 3 to 4 times what we saw last year. Some of the US models in the Pacific Northwest are suggesting 5 to 6 times. So not all the models are in agreement, but it's not a very rosy picture. We're going to see a lot of fire in the future. So as Paul mentioned, our landscapes are synchronized for large fire and repeated large fire. We've got lots of silvicultural process treatment produced fuels. We have a lot of insect and disease fuels. We have burned areas, Ogmas, Ungulate Winter Range, places that we haven't dealt with properly. We've got lots of logging slash out there. We have recently burned areas that we didn't salvage or do restoration treatments on. And we have things like utility corridors that are full of slash. We've done a lot of vegetation management in the province, and we haven't given a second thought to the fact that it's fuel. It's fuel for fire. So we don't have a lot of natural breaks out there anymore. We have a contagious landscape. So I'm going to talk briefly about some very interesting research that we've been working on, Paul and I and Susan Pritchard from the University of Washington and Paul's team at the lab in Wenatchee. And we're looking at what's called reburn research, and we're trying to get a better understanding of wildfire resilience and the various types of patterns out there that impede fire flow, that they impede the contagion of fire. And one of our studies here is, how do the location, size, and age of past wildfires influence subsequent wildfire behavior and effects? And were past wildfires effective as barriers to subsequent fire spread and severity? And one of our study sites, one of our case sample sites, is the Tripod Complex of Fires in central Washington in 2006. Our other 2 sites are the Kootenai Complex of Fires in Kootenai National Park in 2003, and the East Zone and Cascade Complex of Fires in central Idaho in 2007. And this one's very interesting. You've got kind of a typical fire severity map here, but one of the things you notice is that the fire didn't burn through previous fires. We've got the 2003 fire up in the right-hand corner there. That was the Farwell Canyon and Isabel Canyon's fires. The 30 Mile Fire, which was in 2001. Thunder Mountain Fire in 1994. And that little round donut down in the lower left-hand corner was the Forks Fire, which was in 1979. And the fire slammed into that Forks Fire in 2006, and it didn't reburn it. And one of the issues was that fire was actually a reburn of a previous fire. And there wasn't a lot of fuel. That upper right-hand box up there is actually the fuels in the Forks Fire imprint on the burn scar. And as you can see, there's not a lot of surface fuel. But when we look at a lot of the non-high severity patches, the green patches, when we investigate those things, we want to see why didn't the fire burn that, what was it about the fuel characteristics or the stand characteristics that basically made it an impediment to fire flow? And we certainly had areas down in the mixed conifer, the dry mixed conifer, where they had done thinning and prescribed burning, and those places didn't burn. We had the Forks Fire, which was a reburn that didn't burn. Interesting one is that the second one from the top on the far right is a 90-year-old lodgepole pine stand. And it was about a 300 hectare patch, and the tripod slammed into it on a really good burnable day, and it didn't burn through it. And when we investigated it, there's just no surface fuel. it had burnt in the past, and it reburnt a couple of years later, and it consumed all the large fuel, and then it grew a lodgepole pine forest. And we've all probably walked through a forest like that. It's nicely stocked lodgepole pine forest. It's got a lot of grouse whortleberry in it and black chunks of wood on the ground. It's a non-burnable patch, and they'll persist on the landscape, and there was actually a lot of those. And we also found down there that we had a lot of old silviculture blocks that were clear-cut or seed tree or shelterwood blocks that had been prescribed, burned, and planted, and they didn't burn either. So when we do these sort of forensic analysis of these burn areas, we get an idea of what are those resilient structures and patterns on the landscape. And reburn, as Paul alluded to, is a big part of that. It's something that it's kind of new to our lexicon. What is a reburn and what does it mean ecologically? So I'm going to give you an example here from Kootenai National Park in 2002. And that was the Shanks Fire. And it burnt a couple thousand hectares of the park. This is what it looks like in 2010. Lots of dead trees, a fair bit of lodgepole pine regen coming in. It's kind of spotty in a few places. Well, last summer in the 18,000 hectare Verdant fire, it reburnt. And it burnt pretty hot. And this is what it looks like about 3 or 4 days after the fire. Lots of white ash, consumed most of the dead and down material. And this is a proxy of what it's likely going to look like in a couple of years. It's going to be grass, herbaceous, shrub, and as Paul alluded to, that's a natural pattern on the landscape. And it's likely going to be in that pattern for a while. It may actually get caught in a loop in that pattern as subsequent fires keep reburning and regenerating the grass, herbs, and shrubs. But that was basically a natural pattern on the landscape, and we're getting to see a lot more of that. Scale is an issue. This example here is from central Idaho, where we're on a tour 2 weeks ago, and that's several 100,000 hectares. So we don't exactly want that scale, but we do want those patterns on the landscape. They do have form and function. So I also want to talk about stand dynamics and fuel bed succession here, and Paul had an earlier slide of these stand structure type diagrams, so I'm going to walk you through this for those of you who has been a few years since your stand dynamics class in university. So this is our post-disturbance stand initiation structure type. We've got lots of regen, we've got a few persistent residual trees, lots of snags. And then over time, once the canopy closes, we have stem exclusion closed canopy structure type. And a little bit more time, a little bit more disturbance, breaking up the canopy gap. We start to get a few more trees coming in understory, and this is understory reinitiation. A little bit more time, a few more layers come in. This is young forest multi-story. And then we have old forest multi-story in our moist types. And then we have old forest single story in our dry types. And this I'm getting to something here where we can actually use these for some use. So we're going to look at succession trajectory, fuel load, and potential fire intensity under a couple of different management scenarios. And the little individual, the y-axis on here is fire intensity, and that's in kilowatts per meter. And for those of you who aren't fire people, the little guy down the corner with the Nomex on and 400, that's the extent of which hand crews can tackle that level of fire intensity, about 400 kilowatts per meter. 2,000 kilowatts per meter is about the extent of equipment, dozers. Well up to 40,000 kilowatts per meter, that's basically a rank 6 high-intensity crown fire. So post-traditional harvest and replant, we have lots of grasses, herbs, and shrubs, and lots of surface fuel remaining from the harvest through stand initiation into stem exclusion and then on into understory initiation, at which point a lot of those fuels have decomposed and they've gone away. But once the canopy starts to break up, and we have more stand mortality, we start to build in fuels again. So from a fire intensity perspective and risk perspective, this is what the curve looks like. And you have to excuse the free form on there, but it was after a bit of coffee that morning. But basically, we start out at more than 2,000 kilowatts per meter the year after treatment, with that surface fuel load. And we take a little bit of a dip once the canopy closes and some of that fuel starts to decompose. And then once the canopy breaks up again, we just head on a trajectory up to 40,000 and more. So that type of treatment scenario leaves us at high risk for the rotation. We do silviculture treatments and we plant trees. We're carrying that risk for the entire rotation. there's no point along that process when we really have low risk. We have high risk the whole time. This is a wildfire and no salvage and replant scenario. So we actually have a brief period here of bare ground. And some of our research shows that post-wildfire we can gain a year or two where it's not going to regrow and reburn, sometimes 5 years, depending on how hot it burned or the ecosystem it burned in. But eventually we start to rebuild that fuel complex again, and we have, like I said, we have that brief period of low risk, but basically it climbs, short dip again once the canopy closes, but it just stays high and keeps on going. So that scenario is also full of risk. And finally, this is the reburn and replant. So the two little arrows down here in the bottom represent two disturbances, a wildfire followed by a wildfire a couple of years later. We carry no large fuels through this scenario, through the rotation. We have a period of bare ground that may last up to 15 years in some places. We've done some research and showed that those reburn sites will not burn again for about 15 years. We go through a period of grasses, herbs, and shrubs, but you'll see that fire intensity stays low through long periods of time under that scenario. And then mostly it's because we don't have any large fuels. We have a period of grass and fine fuels that's there, flashy fuels, we can capture that. Once the canopy closes, those fuels are gone. So we go through another nice long period during stone exclusion of very low risk. And those become some of those resilient patterns that we need on the landscape that we don't have anymore. And so here's some ideas of these periods of inflammability. So a reburn site, based on the research, 5 to 15 years. We don't have enough research yet. It's kind of scattered all over the place. Those closed stands of mature forest on reburn sites, 40 to 120 years. We sampled some stands in Kootenay National Park of subalpine fir and spruce on reburn sites that were 180 years old. And there's still no surface fuel, there's no ladder fuels. So that's basically a pattern that we can work with on the landscape. And pure hardwood stands, pure aspen stands, as long as they stay healthy, 40 to 80 years. So we need to start looking at these patterns and processes scattered across our landscape as barriers to fire flow. And where these things occur is also really important.